Oh hi! Welcome to the next video in our series on thermodynamics. In this video we're going to talk about the important concept of energy. And as I told you in the introductory video, the concept of energy, its existence, is guaranteed by the First Law of Thermodynamics. Now the law does a little bit more than that. It doesn't just define that energy exists, it also tells you what it is, how one can measure it, and how it is related to the other concepts of thermodynamics. So it's a very important law because it glues many things together, but for us right now the most important thing is that it defines what energy is and that it can be defined in the first place. Now this might sound a little bit mysterious or cryptical to some people, because why wouldn't we be able to define energy? I mean, at the very least, energy is used in everyday speech, so obviously it's a thing that exists, right? Well, energy suffers a little bit from the fact that it's also used as a word in everyday speech, but that meaning has absolutely nothing to do with this definition of energy. Let me give you an example. Suppose that you wake up in the morning and you really don't feel like going to class. Then one can say in everyday speech, man, I don't have the energy to go to class today. Now, that has nothing to do with this concept of energy. It's just another way of saying I don't feel like doing something. By the way, it also works the other way around. If you do feel like doing something, I have an enormous amount of energy to go do out this and this, something like that. But that, of course, is not what we mean by this energy. Another example of where energy is used in everyday speech is to signify what the atmosphere is in a certain location. Yes. Suppose that you go into a room and people over there just had a fight with each other, verbal fight, and you can tell that these people don't like each other very much at the moment. You can come in and you have all these subtle hints that some fight had happened over there. You say, man, that room over there was really bad energy in there. By this you just mean that the atmosphere wasn't very good, but again has nothing to do with this concept of energy. So energy comes a little bit with the disadvantage of already having a usage in everyday speech, and that makes it a little bit obscure to also apply the same word within physics. But of course we need a rigorous definition for it. Now, people who have already done some natural sciences are probably used to the concept, at least in formula form. They probably have used the concept many times over to do calculations. So let's go through a list of these just for a little bit of an overview. Then I will tell you that there's something with that list that needs addressing, and that we will do with the first law. For instance, here's an example. In classical mechanics, right, the studies of how masses move due to forces, there is a concept that is called kinetic energy. And the kinetic energy, sometimes depicted by capital K, is really just given by the mass of your object, my book in my example, times the velocity with which it is going squared, and then half of that number. So here's something that we call the kinetic energy. Okay, I'm sure people have seen this before. Another example of a formula for energy is the energy due to gravity, due to height. If I take my mass and I suspend it in gravity, say h meters from some reference point, let's take the floor as a reference point. We don't need to, by the way, the reference point can be anywhere, but let's take the floor for definitiveness, yes? There's a certain height, then one can calculate a number. It's called the potential energy, or the energy due to height, or the gravitational energy. It goes by different names. It just is the mass of your object times your local value for the acceleration due to gravity, which close to the Earth is 9.81 meters per second squared, times the height with which it is suspended from your reference point in a gravitational field. Then you have something that I'm going to call the gravitational energy. Okay, I'm sure people have seen this one before too. Other examples exist too. Suppose that you're in quantum mechanics and I give you one photon, which is one particle of light, and I ask you what is its energy. And people have found out that the energy of one particle of light is given by a number. It's called Planck's constant. It's also called h, not to be confused with this one. Different number. And times the frequency of the light, the color of the light. Blue light has a higher energy than red light does, according to this formula. And depending on your field of studies, I'm sure you have seen many other examples, formulas that give you a number that we collectively call the energy. So I'm sure people have done calculations with these sorts of things, so they are probably pretty used to thinking about energy in the physics, chemistry, biology sense of the word. But here's a couple of things that need addressing. One of them is, First of all, where do the formulas come from to begin with? Somebody told you that the kinetic energy, whatever it is given by this formula. Okay, there's a formula, and nobody tells you where it comes from. Another one is, okay, where does this formula come from? Why is it m times g times h? Same with this Planck's formula, the energy for photons, and all the other ones you can care about. So that's an issue. Where does this energy come from, these formulas? Second question that one can ask here is, okay, I have all these formulas now, the whole list goes on and on and on. Why are they all called energy? Why do we, by our usage of the word energy, give the impression that it's all the same stuff? I mean, it's numbers, I can see that, but I see no reason why I should all collectively put them in the same bucket and all call it energy. Why is that the case? How do we know that this is really the same sort of stuff as this one and this is the same sort of stuff as that one? The formulas don't look anything alike. So why is it the same stuff? How do we know that that is the case? So that's a point that needs addressing. And the final point that needs addressing is, well, we have a whole series of formulas that, again, for some reason we all call energy. And if you take them all together and you add them, then some final grand total comes out, and that number should be conserved, as in that number is not allowed to change. Why is that the case? Now, I'm sure many of you know the formulas and know that it is conserved, but I hope to have conveyed to you now that there's really some questions there. So that needs addressing, and again, this is what the first law does for you. I'm going to erase this, and just to warm up a little, what I'm going to do is I'm going to derive at least one of those formulas for you right now in a very particular setting, namely Newtonian Mechanics. And I need that example because then I can show you that maybe this derivation cannot be used for any other ones. And again, to hammer the point home that we need an underlying structure. So let's take classical mechanics again. I'm going to take my book and I'm going to suspend it in air, and somebody has told me, you know what, let's start with this number. That's this book. I'm going to draw the book here. It has a mass m, and I'm going to suspend it with respect to the floor at a height h. Okay, then that book we can assign this number h, m times h times g to. All right. Now I'm going to drop the book. The book is going to fall down due to gravity. Then let's draw an axis here so I can point out moments where it is. And let's say that at some point the book has fallen to here. And that height, with respect to the floor, I'm going to call h primed. A different number than this one, and obviously this is a smaller number than that one. The difference between those two heights I'm going to call delta h, literally the difference between these two together. Now, my question now is the following. What will the velocity be of the book when it is crossing this h primed height? Now, people who have studied classical mechanics will give you the answer. They will say, well, if it had m times g times h of energy at this height, then at the moment that it will cross this height, the total energy will be m times g times h primed, the height energy at the new lower height, plus a different number that we called the kinetic energy before. Here's the velocity with which the book is passing this new height h primed, and setting this number equal to this number. So saying that whatever comes out of this should be the same number as this number. Knowing what the original height was and what the new height is, the only unknown in the formula while you set these equal to each other is the unknown number v. And you can use your basic, very simple mathematics, get the number v, and then you know, oh, the book has this velocity v at the moment that it has passed this. This is a very simple exercise that I'm sure everybody has done in high school. Now, my goal now is to derive this, that this is the case. So I'm going to pretend that I didn't know that the difference between this number and that number is mopped up by 1/2 mv squared. I'm just going to derive it here on the spot. It's not that hard actually, because look, this h this h is given by this number plus that number. So I can replace this h by h prime plus delta h. This I can just read off from my little picture here. I'm going to split this up. Right, and just work out the brackets, and then I get m times g times delta h. No physics has been done at this point. The only thing that I did was I replaced this height by the sum of these two, and I just worked out the brackets. Here's where the physics comes in. Because there's a delta h here, which is how much the book has fallen. And how much the book has fallen, if it is under constant acceleration, then Newton's laws tells you how much it has fallen. So here's a little side note. In Newton's laws, you have that the acceleration times the mass is given by the force that the mass feels. In this case, that's gravity, and close to the Earth, that number for gravity, gravitational force is m times g. So Newton's second law gives you that m times g is equal to m times h. That tells you that the acceleration obviously is going to be g 9.81 meter per second squared. But it also tells you that the thing has a constant acceleration. Now, if it has a constant acceleration, you can calculate how many meters it has fallen. That is my delta h. So from this result, I can calculate the amount of meters that it has fallen. It's actually quite simple because look, the acceleration is nothing else than the derivative of the velocity. So I can turn this formula that tells me the acceleration, I can turn into a formula for the velocity. I have to do the opposite of derivatives, which is integration. So I can just integrate both of these sides. That gives me a times dt equals g times dt. And since a is a constant and g is a constant, I just get this. And then I get that a times t is g times t. And a times t, well, I did the opposite of derivatives, which is integration, should give me the velocity. So the velocity that the book will have when it gets here is g times t. This is not surprising to anyone who has done any high school physics, obviously. But I can do a little bit better still, because if I want to continue with this formula, I need delta h, how much it has fallen. Right now I have the velocity with which it is falling. I need how far it has fallen, how many meters it has made. And I can use the same trick again. Because I know that velocity is the derivative of the position. So that means that if I want to get the position from v, I need to do the opposite of derivatives, which is integration. So I can integrate this formula one more time to get the amount of meters that the thing has fallen. So if let's continue here for a moment, this is what I had. Let's integrate it one more time, and then I get the actual meters that the thing has fallen. So I can put an integration here. There we go. This then by definition is how much it has fallen. Let's integrate this guy over here. I hope this is no difficulty for anyone, because this will give you 1/2 gt squared. That's my delta h. Good. So over here I just went a little bit into Newtonian physics for the only reason to get my delta h here replaced by something else. And in fact I can do a little bit better still, by the way, because I see gt over here, and at least one of those gt's, well, you know what, I'll go there in a second. I think it's easy to continue here for a moment. Alright. So the important formulas that we have now is these two. I'm going to erase the rest just to make a little bit of space. So we've used the concept of integration now, and with that I can replace delta H by 1/2 GT squared. That's this formula. And if you look closely, you will see that this has become 1/2 GT squared. Right? There already was a G, and together with the G that came from here, I get a G squared, so I can put the G and the T in one big square. But the thing between the brackets here is what I call V. I derived that to be V. This is a step that I wanted to do a second ago and decided to do it now. So let's do that. So from my Newtonian physics, I know that GT squared is the same as V, and I get 1/2 mv squared. In other words, here's the formula that I can use to calculate how fast the book is going once it has passed from here and goes all the way to here. And this is the formula that people use in high school. The difference between the two height energies is mopped up by this new thing called the kinetic energy. Now, what is the point here? The point is not that you know how this derivation goes. The point is that I was able to define something that gives me physics. I started with this thing. I did Newtonian physics, Newton's laws, F equals m times a, and some integrations, and I found this new law. And then one can simply say, you know what, since we have this law, might as well give it a new name. We're going to call this the energy of the system, and it must be conserved because the difference between those two height energies must be compensated by something else. So I really derive now the law of conservation of energy, and I've defined what energy is. But I haven't done any new physics. The only thing I did was I just did Newton's laws in a new mathematical formulation. It was just Newton's laws and some integrations. So the big point here simply is there are systems where it's quite obvious that one can define energy. But this particular derivation only holds for this particular system, for a mass falling under gravity, and in a situation where Newton's laws hold, because that's what I had to put in to get to this result. So it's a nice definition of energy and the conservation of energy, but it's not very general because it only applies to this particular situation. So we have to do better. Here's where thermodynamics comes in. I'm going to do the following. As per always, in order to define energies, what I need is some system to point at. As I told you in the introductory video, I'm going to typically take gases because that's the historical go-to example, but it's not because what comes out is specific to gases, it's simply because I need something to point at. So, if you're uncomfortable with that, replace the gas by a banana and everything that I'm going to do applies just as well. So here's my gas. I put it in a barrel. The barrel has a lid. And the lid is slidable. Here's the lid. You can slide it up and down, and for the sake of convenience I'm going to say that the sliding is done without any friction. So there's no friction between the sides of the lid and the sides of the container of the barrel. You can make your life difficult to want to include this anyway. Let's not do it here because that's not where the point lies that I want to make. So here's a gas, or your banana. The point here is that I have some piece of nature and it has a volume. It probably also has other features. Yes, a gas typically would have a pressure. By the way, bananas and cats and other things that are in volumes also have pressure. So there's probably going to be a pressure and there might be some other observables too. Okay, I only need the volume to get to my point in a moment. So I'm sure we can all agree that every system that you care to look at in nature at the very least is contained within something, has a volume. Okay, so I have this here now. So I have a gas that comes with some number for its volume and some number for all the other observables that might be in there, for instance the pressure. But now I want to change the situation. I want to change my gas into something else. Well, it's still a gas, but that these numbers are going to change. It has to be in a different state. Suppose that I want to change the volume. Then one thing that I can do is, for instance, push on that lid. By the way, a slidable lid in this context is typically called a piston. So I'm going to use piston and lid interchangeably. So I can push on that lid. I can put a force on there. Yes, I can push. Okay, well, if I do that, then later on, means a moment later in time, I have the same barrel, but now the lid, the piston, is going to be over here. It's going to be a little bit smaller. So there's a difference in where the lid was and where it is now. And well, obviously the volume of that system is going to be a different number. So that I'm going to call V2, some number, smaller number, V2. The other observables probably have changed as well. How they have changed, well, that depends on whether it is a banana or a gas and what the properties of the banana or the gas or the cat or whatever it is that you're looking at. So how the numbers change, exactly what new numbers comes out, that is dependent on the specifics, the microscopics of the system. But the fact that they do, that is quite general. So I'm just going to say all the other observables, no matter how many they are, I'm going to label with the number 2, means after I did the pushing. Okay, now I want to have a number that tells me how much pushing I did. What is the amount of pushing that I did? And one number that one can think of would be, well, let's take how much force you had to put on the lid times how much the lid has slid down. One can define that as the amount of total pushing that I did. The amount is going to be bigger if I had to push hard. It's also going to be bigger if I had to push further. And that seems like a reasonable starting definition of my new concepts. So that number, I'm going to give the name capital W. In thermodynamics it's called the work. It's the work that you did. Now that number by definition is the amount of pushing that I did, F times how much the thing has moved down. In this case I'm going to call this amount of pushing down, how much the lid has gone down, I'm going to call that X. So I just defined a number here. Yes, there's no physics, just a new definition, but it's a sensible definition. It feels like the correct definition for how much pushing I did. Now, it's an okay definition, but I would like to extend it a little because in my example over here, the pushing happened only in one direction. It just was downward. But in principle, if I had any piece of physics, again, let's take my stupid example of a banana, I can also push the banana in different sides. I can squash the bananas, not just in one direction, but also in the other directions. So maybe we should extend the definition for work in such a way that it doesn't tell you how much pushing you did in one direction, but in all directions. In other words, how much the volume has changed. So that's what we're going to do now. We're going to extend this definition to incorporate the fact that this pushing in any direction ultimately will come down to a change in volume from V1 to V2. Here's why I want you to note that by making this step, I'm making things very general because changing volumes also happens when you squash bananas or cats or what have you. Now here it's quite easy to see how I can turn this into a change of volume. Quite simply actually, because look, the lid, suppose that it has an area of A, so many square meters the lid was, then the change in volume, how much the volume has changed, well here's where the lid was, this is how much, or where it is now. The space in between is how much the volume has changed. And then you take your very basic mathematics. I just want the volume, the stuff inside, the amount of space inside those two positions of the lid. And you can easily read off, again, high school mathematics. You just need to have the base, the area, times the amount that you made it slide in one direction. So I can easily read off that the volume, well, let's call it change in volume, a dV, so the dV is how much the volume has changed, that's this number, is given by, well, the area times the amount of sliding of the lid. And let's also put the d's over here, by which I'm now going to mean the amount of volume change. I can easily turn this dx into a dV by this observation over here, and then I get an F over an A times a dV. And an F over an A, that is what we call in physics a pressure, the amount of force you exert on an area. So this guy, F over A, is by definition what we call the pressure times dV. So just to be sure, the only thing that I did here was I took some definition for how much pushing I did and I extended it such that this pushing definition applies to changing volumes rather than just pushing in one direction. But it's all the same thing anyway, right? But this makes it just a little bit more general. Small final comment to my definition for work is people define it with an extra minus sign. They do this for a reason. The minus sign is because we want this number to be positive. Remember, work means how much I had to do, and how much I had to do I want to come out as a positive number. That if I did something, that number should be a plus number. But in my example here, you can see that if I push the thing down and make the volume smaller, then the change in volume is itself negative. dV, this guy over here, is a negative number because it tells you how much the volume has changed. Well, it has changed negatively. I went from a big volume to a small volume, so dV is negative. So if I know that dV is a negative number, but I want my definition to give me positive numbers if I did pushing, then the negative number that is in dV should be compensated by an additional minus sign over here. So, all of this is just me introducing a new concept for amount of squashing of a system. And that amount of squashing is what we call the work. And as we have seen now, the definition for this is the pressure, how much pushing I did per area, times the amount of volume change that I made. And again, works with bananas too. I squeeze on a banana, I have to exert pressure on the thing, the volume of the banana will change. As you all know, you squash a banana, you will see that the thing will have a different volume. And the amount of work that I had to do for this is not given by that number. Okay, so that's quite interesting. Now, here comes a problem with this particular definition, and this will lead us to the concept of energy. This number tells me, well, if I push it down a little bit, that's what the D meant, and I made this small amount of pushing. But if I do a big amount of pushing, what I need to do is integrate this. I have to add all the small amounts of pushing. So the total work that I do has to be the integral PdV. That's the total amount. No problem so far. This is just me going from small pushes to one big push, which is a sum, that's an integral, of a lot of small pushes. But here's where a problem starts to arise. As you know, integrals, the outcome of an integral means the area underneath a curve. So let's draw a curve and look at the area underneath, because the area underneath is a visual representation of what I have now called the work. So I'm going to make a PV diagram. Again, it happens to be a gas, but it works for other systems as well, because all systems come with pressure and with volume. So the gas is just for me to point at. Now, I started with a starting position V1 and a starting pressure P1. And well, I'm just going to draw a dot over here. Let's make it this one over here. That corresponds to V1, some number, and correspondingly P1. So this dot over here, my PV diagram, means the original state of my system, my gas. I did some pushing, and then I end up with a smaller volume and with a different number for the pressure. So the volume has gone from here, a big number, to the left where it becomes a smaller number. And let's say that the new volume V2 is over here. As you can see, it's a smaller number than V1 as per my example. Now, what the pressure did, well, actually, I don't know. Over here, I just drew it down here. My example, apparently, I was thinking about something that I press on it, and the pressure actually becomes a smaller number. Now, this might not sound like a gas to you, because if you press on a gas, typically the pressure will go up. So if you really want to stick to the example of a gas, then what you might want to do is get this pressure 2, P2, and put it above pressure number 1. This is very specific to a gas. If it's not a gas, but some other system, you could easily have that the pressure also goes down as the volume goes down due to the pushing. It doesn't matter for my example, so I'm going to stick this number here. If you're comfortable with it, put the number over there and you will see that my argument will still hold. Okay, now, so this is my beginning state 1, this is my ending state 2, from here to here. Now the question is, how much work have I done to make this happen? And since work is an integral, it has to be the area underneath the curve. But notice I don't have a curve yet. I just have the beginning point and the end point. So I have to define a curve. How did I do the pushing? So let's start with, I'm going to use the red marker for this. Let's say that the way that I did the pushing was like this. That I pushed in such a particular manner that yes, the volume went down, but the pressure also went down linearly using this straight line downwards. Okay, don't ask me how I did it, that's not the point. Just the fact that I, in principle, could have found some way of doing it in this way. Okay, then the work is the area underneath that curve, which would be this area. So this would be the work, the W, this area, that corresponds to me having pushed my system from this volume to this volume in this particular manner. Okay, some number comes out. Alright. I'm going to use a blue marker now, because there's also other ways that I could have made my gas go from here to here. Maybe in some other practical way, the way that I went from 1 to 2 was like this. Again, don't ask me how I did it, that's not the point. I can think of ways, I can make a machine, I can do the pushing in a very particular way such that now the pressure will also go down to this new point, but just using a different path. Now, then the work that I did for that particular situation is now the blue area. And as you can see, the blue area is a bigger number than the red area. And that's the point that I was building towards. It tells you that how much work I had to do highly depends on how exactly I did my pushing. I can make the volume change, but how much effort I will have to do, how much work I will have to do depends on exactly how I did it. Okay, so this is just mathematical fact that comes out of this. But unfortunately that means that maybe this is not a very useful definition. Because apparently I can make this number come out whatever I want. Some number came out for the red curve, another number came out for the blue curve. Maybe if I did it in a different way still, like this for instance, then the curve that's now green, that area is smaller. So I can make W come out whatever number I want. I just have to adapt the way that I push and pull. Now, why is that a problem? It's a problem because that means that the letter W doesn't really mean anything. If I tell you that I had a gas in this system and I told you how much work I did on it, you do not know what my final outcome is. That only works if every beginning and end situation has only one number that comes out for W. If that number is not fixed, as we can clearly see that it isn't, it simply means that the word W has very little physical meaning. So that's too bad. We have a definition that we cannot really use. So I want to hammer this point home by looking one more time at the example of my book. So with my book I don't have this problem. Here's my little book corner. Yes, my book example. If I want to calculate, so I lift up my book like this, from the ground to this height h, then let's calculate how much work that cost me. Well, the original definition of work, if you recall, was F times dx. F is how much force I put in it, dx is how much, over what distance I had to do the work. Now the F that I have to put in is at least the gravity, otherwise I cannot cancel out the gravity downward. If I want to bring the book upward, then the F that I have to supply must be at least gravity and preferably higher. So my F must be at least m times g. dx again is how much I lifted it up. This is for a small amount of lifting. If I want to have the total amount of lifting, I have to integrate the dw. M times g is a constant, goes in front of the integration. I get a dx here. Well, the integral dx is just the sum of all the small amounts of lifting that adds up to the total amount of lifting. And the total amount of lifting I called h. And I get that my book lifting is given by n times g times h. By the way, that's exactly the definition that I used when I was doing this Newtonian Mechanics on my falling book. I started with this definition, and now you see why I did it. I took the work that I did to bring the book up there, and then I showed that when it fell down, you get 1/2 mv squared. So that's why I came up with that starting definition. But here's the point. In the lifting of my book, as we can see in this very small book corner over here, I didn't have to say how I lifted the book. This integration did not care whether I brought the book up like this or that it brought it up like that. Those are different ways of getting the book from position 1 to position 2, yet the integral gives me the same number. So in this example over here, work is a useful number. It doesn't care how I did it, it just cared what the beginning and end point was. So that means W is really the same number regardless. So it's a useful number. It's a number that one can use. It has meaning. Not here. Here we saw that how you went from position 1 to position 2 is dependent on how you did it. And that made it a useless number, because here, as opposed to here, the work could have had any value. So clearly you can see that work in some contexts is a good definition, and in some contexts it isn't. Now let's go to energy as a definition. We define energy in thermodynamics as the number that does not care about how you did it. Energy in this case is the number that doesn't care how you did it, like in my lifting of the book. So here is why I simply call this the energy. It's because it's a useful number. The number can only have one value for this particular situation. It's a useful number, and that useful number I call energy. In fact, going back to my Newtonian Mechanics of the falling book, I actually did so. I called this guy the height or the gravitational energy, and now you see why. So the definition of energy in thermodynamics is the amount of work that you have to put in to go from position 1 to position 2, but only if that number that comes out has only one value. That it doesn't matter how you did it, it only matters what the beginning and end point was. That's what we call energy in thermodynamics. So clearly, we cannot define energy here, because there is not just one number, there's a whole range of numbers depending on whether you took the blue, red or green path. So energy here cannot be defined, it seems. Here it can, here it cannot. Well, that's too bad. Fortunately, there's a way out. Because if there's not a way out, we can never work with energy in thermodynamics, only in isolated cases, for instance in my Newtonian physics. Fortunately, there's a way out. And that was found by Scottish physicist James Prescott Joule. And Joule found out that, well, let me just draw it, that's easier for now. Joule knew that one can also make a gas go from position 1 to position 2, not just by pushing on it, as I just did in my picture, but of course also by the zeroth law of thermodynamics. You can also change the system of a gas, the state of the gas, by the zeroth law. And if you remember from the previous video, the zeroth law doesn't require pushing or pulling. The zeroth law just says, take your system, put next to it some other system, and then nature will do something, we call that heat, to make the system change. So Joule knew about this, of course. He knew that I can change the gas from position 1 to position 2, not just by pushing and pulling, but also by the zeroth law. And he had a brilliant realization. He thought maybe the work will give you different numbers depending on how you do it, but maybe the difference in those three types of doing it is supplied by the zeroth law. Maybe W, the work, is not a fixed number, but maybe the sum of work plus the heat that is applied, that grand total, that one actually is a number that always comes out the same. So he did experiments. He literally took gases and liquids and he pushed on them and he measured how much heat went in and out, and he looked at all the 5 million different ways he could go from here to here, but not just looking at the work, but also looking at the heat. And then indeed experimentally he found that the amount of work that you had to do to make the system go from position 1 to position 2, this, as we can see here, is not a fixed number, but the amount of work plus the amount of heat, that this guy is always the same number. And that means that this cannot be defined as the energy, as it could here. This cannot be defined as the energy, but their sum can. This is the first law of thermodynamics. It tells you that the work amount to go from 1 to 2 is not fixed, the heat amount is not fixed, but their sum is fixed. It's an extremely important conclusion. Now, for people in in current day education in the natural sciences are not surprised, because heat is a form of energy. Yes, but people didn't know that back then. The only thing that people could do, like Joule was looking at a system in position 1, system in position 2, and wonder what happened there. They didn't have formulas for energy. They didn't have the notion of energy. They didn't have the notion of work. They didn't have the notion of heat. So somebody had to get that all together, do experiments, and find that actually they are the same. So please forget that you were already taught maybe that heat is a form of energy. It was discovered for the first time by Joule and his contemporaries back in the day. So there's a couple of things that now went on here. So just to reiterate, and then we're going to wrap up. What is energy? Energy is, well, the sum of work that you had to put into a system and the amount of heat that you had to put into a system to make it go from position 1 to position 2. That is the definition of energy. And the important thing is, and that was the whole discussion here, that if that number was not just dependent on position 1 and position 2, but also on how you did it, that number would be useless, because that number could have been anything. The fact that experimentally you find that the sum is always the same for a given beginning and end position, so that makes that this number not useless, but actually a fixed number. That is the first law of thermodynamics. If he had not made that discovery, taking this as definition of energy would be a useless definition, and taking this as definition of energy would also be a useless definition. So this defines energy, and it tells you a little bit more than that too. And let me wrap up with some final comments. By the way, notation wise, I put a little bar through these, and that is in thermodynamic text to signify that this guy integrated, that this guy integrated might give you different numbers depending on how you did it. It's called an inexact differential. Now, if you don't care about the terminology, don't worry about it. The gist is in what we just discussed. So, a couple of final comments. This observation by Joule and his contemporaries shows that energy can be defined in a useful way. That's number one. It also tells you that energy is made up out of two things: the amount of work that you did and the amount of heat that was supplied by the zeroth law. It also tells you, and that's a very important one, that heat and work are apparently two types of the same thing. They belong to the same bucket. And why is that important? It's important because it tells you that in principle one can swap heat to work and work to heat. And that's the principle, if you will, of a steam engine. Now, we don't use many steam engines anymore, but this was the principle that was behind steam engines, because people realized that, wait a minute, if you can turn heat into work, and work just means pushing and pulling, you can turn some of this stuff into pushing and pulling, say, of a train, and you can make a train go. The realization that heat can be turned into pushing and pulling and therefore make machines was, of course, the gist of the Industrial Revolution. And that's also what this law tells you. The fact that you can swap them around, because their sum needs to be this thing, but within that sum you can swap around as much as you want. That was a big realization. And that leaves me with a final question. If one can swap heat to work and work to heat, at what ratio can this be done? In other words, suppose that you have a certain amount of heat. Can you turn all of that heat, the 100% of it, all of it into work? And the opposite question is, if you have work, can you convert all of it to heat? It's the same stuff, so they can be swapped into each other, but by what ratio? Is there a cap to it? So we're almost done with understanding heat and energy. Just for that last question, how much swapping can be done between the two concepts? And that is the second law of thermodynamics. I will foreshadow a little bit. We will find that yes, it's always possible to turn all the work into heat, 100% if you want, but it's impossible to turn all of your heat into work. There's a certain amount of energy that's trapped into heat that cannot be transformed into pushing and pulling. And that is going to be the second law of thermodynamics. So in the next video, I invite you to look at it and see exactly how the swapping goes and what its cap is. For now, we have dealt with the first law of thermodynamics.